Just one moment, guys. Sorry for the delay. Okay, so good afternoon. To start off with, congrats on being here and welcome to the second lecture of the day. After an exciting session on gravitational lensing, we now have yet another thought-provoking session on the geometry of vision. The speaker, Dr. Vijay Ravikumar, was a professor at the Chennai Mathematical Institute, who is forever known for his unique and intuitive approach to teaching. He completed his PhD from the prestigious Rutgers University in 2013, and his research interests include Schubert calculus and algebraic combinatorics. Known famously for his immense passion for art forms, he is now a part of a drama troupe, Perch, based in Chennai, and is touring all over the world, staging plays. So today, Dr. Ravikumar will draw your attention towards some seemingly counterintuitive tricks our vision plays on us and the beauty of mathematics behind it. So curiously titled The Geometry of Vision, we all eagerly await what's on the store for us today. So be armed with a paper, pencil, and let's get started on this exciting journey. So over to you, Professor.
Thanks a lot, Anirudhan, and thanks everyone for coming. It's very exciting to talk to such an excited group of students again after a long time. So okay, hopefully the slides are working. So as Anirudhan said, this talk will be on the geometry of vision. And I want to get started by looking actually at some of the history of how we represent our vision on paper. So to begin with, here's an old painting, which maybe you've seen, maybe you haven't, maybe it looks vaguely familiar. It's one of these paintings you probably only see if you've studied art history a little bit or looked through books of old paintings. And it's called The Tribute Money. It's from Italy, 1426. And the special thing about this painting is it's credited as being one of the first paintings to feature something called linear perspective. So something about the way that it's drawn is representing three-dimensional space in what was a unique and new way at that point. So let's just see a few more examples of linear perspective. It'll be easier to understand it through examples, I think, rather than trying to define it right now. So here's a much newer painting, which also uses linear perspective to represent depth and give us a sense of the depth of space. And this is from 1914, so it's much, much newer. And here's another one, which is from somewhere in the middle. So this is from 1665 by Vermeer. And this one, it's much more photorealistic than the others, as you can see. And maybe for today's eyes, it looks almost like it could be a photograph, at least at a glance. So we're actually very used to seeing linear perspective in photographs. So in some sense, it's not so surprising to us. But looking at these, you can see that there's something about the way that they represent space, which it'd be nice to try and capture more precisely. So of course, not all art uses linear perspective. I just found a couple other paintings that I liked, which, for example, don't. So this is a painting from 1981, which isn't attempting to represent space in a way that kind of tricks our brain, at least not in as direct a way. And some artists, they use linear perspective, but they break the rules and play with it. So here's another one from 1914, which, although it uses linear perspective in certain portions, it doesn't all add up in a way that kind of makes sense or sets us at ease. So it's a tool that people can also play with in interesting ways. Some artists even try and blatantly subvert perspective, like David Hockney, when he reverses the rules of perspective to create something that looks almost the opposite of what it should be. So, and of course, for some artists, it's just not relevant whether we're working with perspective or not. So maybe as a question for everyone, does this painting use linear perspective in any way? Just look at it for a second, and is there anything, obviously I haven't defined linear perspective yet, but from what we've seen so far, does it seem to use or give a sense of perspective? And if not totally, are there certain aspects of it there or maybe there aren't. So something to think about. This one is from India from the 1600s. And here's another one from Europe a little bit before that, in the late 1400s, an unknown artist. And this one is interesting in that if you, especially if you compare it to some of the other images we've seen, it's a very different sense of how the space sits than those more photorealistic pictures that we saw, especially starting in the 1600s. So one way to kind of tell whether this is using linear perspective or not is to look at the tiles on the ground. So if you look at the tiles, it's clearly supposed to represent a evenly tiled square floor. And in some sense, if you look at just the tiles there, you see that they're regularly spaced, the angles are right angles, and it looks like it stacks up neatly to give you a checkered tiling. But at the same time, something feels a bit off. And if you compare it to the Vermeer, you can see that in the left-hand side, even though the tiles are evenly spaced, they have right angles, something looks a bit off. Whereas on the right-hand side, the Vermeer tiles are actually all different from one another. Each tile is different from the next one. The angles are not right angles. If you were to actually measure on this page what angle the different sides of the tiles are making, they won't be 90-degree angles. And the size keeps changing, yet somehow our brain interprets this as being a nice, even square tiling. So there's something kind of strange because the left-hand side painting, the tiles are actually squares and they're actually 90 degrees, but it looks odd. And on the right-hand side, the tiles are all different from each other, but it looks like an even 90-degree tiling or even square tiling. So why is that? Why do they look like perfect squares in the Vermeer picture, even though they aren't? Why do we see this and think, okay, this is a square tiling? So it's a bit strange. I mean, we're so used to it that maybe it doesn't feel that strange, but why is it that we see this and we just recognize it as being a nice square tiling? So it's an interesting thing to ponder. Why is it that our vision just knows it? Our brain just makes sense of it. And a little trick you can do when you see an image like this in linear perspective is let all of the straight lines extend. You can just extend them outward, let them keep going, and see what happens. And you can see that in all of the parallel lines, they're converging to the same point. So even though in real life, in space, these lines are parallel, meaning that they'll never hit each other. You can extend them on and on forever, and they'll remain that same distance apart. In the painting, in this two-dimensional picture plane, if you take any of those parallel lines and extend them out, any two of them or any family of them, they'll all touch in one place. Specifically, this family of parallel lines, they all come together over at this point here. And this other family of parallel lines, they all come together at this other point over here. So something interesting is happening. And basically, if I were to sum up linear perspective in just one line, the most important observation is that parallel lines converge. Families of parallel lines all converge together. And that doesn't mean, one family might converge to one point and another family might converge to another point. But given any family of parallel lines in space, in our picture plane, in our image, they'll all appear to converge to a single point. And somehow this is tied in deeply to how our brain processes and our vision processes images, because we know it's correct. We somehow just know that something is correctly representing that evenly tiled floor. And again, it may not seem like such a crazy observation today because we have modern photography and in modern architecture and in cities, we have so many long straight lines to observe just when we're walking down the street. So we can kind of see why we see railroad tracks, we see all of these long lines, which we're used to seeing converge. So it maybe doesn't sound so shocking, but it took a long time to discover because of how different the world was then, and also how people were used to representing space. Maybe people weren't trying to represent it as photorealistically as well. So in any case, when linear perspective was discovered, it had a very radical effect on art. And one question we can ask is why? Why is it that parallel lines appear to converge in our vision, in our picture plane? And maybe, I don't know if anybody has an answer off the top of their head, but it's something to think about. We will answer it eventually today, but I want to let that question sit in the back of our head as we continue. So again, the question is, why is it that when we take a photograph or when we just look out at a scene before us, all the parallel lines appear to converge together to a single point? And a slightly more advanced version of that question is why is it that all of the different sets of parallel lines converge to different points? And what's the relationship between those? So we'll try and answer these questions as we go on. But first, I thought we'll just try an experiment, because it's better if we get our hands on trying to draw in perspective and get a sense of what happens there, what clicks. So I don't know if anyone here has tried drawing in perspective before, tried using linear perspective to draw a representation of the world around them. But let's try to do it now. So to begin with, so basically now is also a good time to make sure everybody has a blank sheet of paper, a pencil, and ideally also a straight edge. By a straight edge, I mean it could be a ruler, but it doesn't have to have any rulings on it. We're not going to use it for measurement. So it could even be that if you have a hardcover book, that'll be fine. Just the edge of a book will also work, or a magazine, something that'll let you draw a straight line or extend a line. So those are the only tools we'll need today: paper, pencil, and straight edge. So if you have one handy, great. If you don't, maybe I'll give you another. We'll continue, and there'll be another moment when you can run and grab one from somewhere else in your house. So as an experiment, let's start with something really simple: the square tiling of the plane. So for example, you could go to many bathrooms have a square tiling on the floor, or maybe even your living room does. But hopefully there's some room in your house or nearby that has a square tiling. You won't need to go there right now, but if you look down and face that square tiling directly, you might see something like this. You might see an even grid. And that grid will be made up of square tiles, perfect squares. And together they'll tile the plane. So you can, even if it's the floor of your room, you can imagine that going out forever. And you could imagine this tiling that plane. And that may not seem terribly exciting, but if you then were to raise your head a little bit or raise your camera a little bit, it becomes a bit more interesting. So the same tiling, if you just raise your head slightly, suddenly it looks like this. The squares are no longer squares. They're now, some of them are trapezoids, some of them are something else. So they're all quadrilaterals, but they're no longer squares. This one, for example, looks like this. So, and taking them all together, we still, tile our plane, but it's now a perspective view of that tiled floor. And now we can make it even more interesting by turning our head a little bit to the side. First, we've looked up, and now if we turn our head to the side a little bit, what do we get? We've turned our head up and then to the side. And now we have an even more interesting set of tiles. We know they're still really squares, but the actual quadrilaterals that each one forms are maybe more interesting, maybe more chaotic, depending on your perspective, but they're different. None of them are squares anymore, that we can say for sure. So as a question, which of these perspective views of the floor do you think would be easiest to draw? Given our tools, we have our paper and pencil, we have a straight edge. Which would be the easiest to draw on a sheet of paper if you don't have the full tiling before you? Maybe a better way of phrasing that, if I give you a single tile and ask you to extend it to a tiling of the entire floor. So on your sheet of paper, I give you a single tile, and you have a single tile to start with. And your task is to extend that to a tiling of your entire page, let's say. What would be the easiest to do? If I gave you one of these tiles, if I gave you one of these second tiles, which are a little more interesting, but still have some parallel lines in them, so there's like some order, or one of these third tiles in the third image, which seem more disordered in that none of the lines appear to be parallel anymore. We know they're actually parallel in real life, but in our representation, they no longer look parallel. So the question is, which of these would be the easiest task to start with one of these tiles and extend it. And which tools would you need in order to do that? So let's actually go through and do each of these tasks. So for the first one, suppose I give you just a single square. How would you go about extending that to a tiling, to a square even tiling? So this one is actually, it would actually require a little bit more than just your straight edge and your paper and your pencil, because you would also need some way of measuring. This square is actually a square. So let's say it has unit 1 side length. So like this is 1 unit, this is 1 unit, this is 1 unit, this is 1 unit. So now if you want to extend it, we have to have a way of measuring a unit. We can, of course, using a straight edge, we can extend all of these lines. We can extend those out. But then how do we know where to mark our next square? You know, you can extend each of these horizontal and vertical lines using your straight edge. But in order to know where the next square ends or begins, you still need some way of measuring. You need some way of measuring that 1 unit along that horizontal line. In other words, on the horizontal line, you'll have to have a way of marking off 1 unit, another unit, another unit, another unit. So for that, you need a compass or some other measurement device, either a compass or a ruler which has markings on it. But you need some way of making measurements. And once you have that, the task is relatively easy. You just extend the edges of the tile, evenly measure out corner points along each horizontal line and each vertical line, and then just fill in your grid. Connect the corners to form a grid. So it's a relatively easy task once you have your measurement device in place. What about this second image though? Now this looks a little bit more interesting. Suppose I just give you this trapezoid-like shape, this quadrilateral here. And again, the task is to extend that to a tiling of the entire plane. Hey, by the way, I just want to mention, anybody can ask questions throughout this talk. It's not that you have to save your questions till the end. So maybe I'll give you this task, but then feel free to ask any questions on anything we've already gone over. So this second image, it's again, if you remember, we started out looking straight down at our feet when we were in the bathroom. Then we raised our head a little bit. So now we're looking at the tiled floor in this perspective. And I'm just giving you one of these tiles now. You have it on your sheet of paper, and your task is to extend this to a tiling of the page. Extend this perspective view. So again, you'd need your compass and your straight edge, because even if the one way to start things out is to extend our lines, extend our horizontal lines, and extend our, which are no longer vertical lines, but are lines that are not horizontal. And when we extend that bottom edge, notice that we still have to have a way of measuring, because we still have to evenly measure out 1 unit along each horizontal line. So we have to evenly measure out corner points along that horizontal line, which means we need some way of taking measurements. So that would be the first task. Use your measurement device to extend and take those corner points. After that, we can extend the left and right edges of the tile and keep extending them upward until they meet each other. And like we saw in that Vermeer painting, they're going to meet, in fact, all of these kind of up-down edges, they're all going to meet in a single vanishing point, what's known as a vanishing point, like we saw in that Vermeer painting. And so we can connect all of those and we can connect all of these together at the vanishing point. We can connect all our corner points to that vanishing point. And this gives us a good way to start extending the tiling. But we hit a roadblock at this point, because how do we complete the grid in terms of how do we add more horizontal lines to our grid? I don't know, I hope this makes sense, what I'm asking. We started with these horizontal lines that are already marked, but if I want to extend the tiling up beyond the photograph, where does the next, I can draw these up-down edges, I can extend these kind of semi-vertical edges to get that vanishing point. But where does my next horizontal line go? I have my horizontal lines from the photograph, but now when I step out of the photograph, when I want to extend beyond the photograph, where would I place my next horizontal line? I mean, it can't be arbitrary. So does anybody have an idea where we could place the next horizontal line?
Sir, will the distances between the horizontal lines be in a geometric progression?
Ah, that's a very interesting question. So what is the relationship between, obviously in the previous example, the distances between the horizontal lines were all 1, correct? Because then when we were looking straight down, they were evenly spaced vertically as well. Now, clearly the distances between the horizontal lines are decreasing. Here it was however long that is. Now it's shorter, shorter still, shorter still. So would they be in a geometric progression is the question. So does anybody have a guess about whether they would be in a geometric progression or what the relationship might be between them, going from one to the next?
Probably the lines will be like homothetic to each other.
Say that again?
They will be homothetic with respect to that.
What do you mean by homothetic?
Similar triangles, basically.
Similar triangles, I see. So that's a tempting...
But whatever parallel line, like whatever line you choose to draw, it will always be similar
It'll always be similar
to the triangle above or below, and say.
So let's be a bit more specific. I guess it's difficult since you can't point. But can you give me an example of 2 triangles that will be similar? Try to, do you mean, for example, we have a triangle here, right? Do you mean, so we have a triangle here with the going up to the vanishing point, right?
Yeah, and then with the horizontal line above that.
And this triangle here with that same vanishing point. So yes, I mean, those will be similar to each other, correct?
Yeah, but I don't see any advantage of it. I don't think you can use that much.
Yeah, exactly. It's very tempting to use it, but it's not so easy to use it once we try. Because again, we need to know where the relationship between this length to this length and to the next length. That's an interesting idea, whether they're in a geometric series. And I won't answer that right now, but that's a very interesting idea. But exactly, we can't, if our goal is to just draw the next horizontal line, let's say, maybe to make the task a little bit simpler in a way, without going into too much calculation, can we draw the next horizontal line without having to make any calculations? That's a question. So rather than getting into geometric series right now, can we draw the next horizontal line without making any actual complicated calculations? Is there a way to figure out where the next one is? And I agree, the similar triangles is an interesting way to start, but where do we go? How do we actually use that? So are there any other ideas of ways that we can know where the next horizontal line should be?
So there's an answer in the chat by Rohan Goyal. I think cross ratio is preserved by taking perspectivity. So repeatedly using Seva Menela's harmonic bundle type idea, we can...
Wow. Yes. So exactly. So everything that he said is correct. But in fact, we can do something really silly and simple in this case in order to get the next horizontal line. So what he was talking about is, he mentioned something about the cross ratio. And that's an interesting quantity, which is going to tell us a lot about what's happening here. But in this case, to know where the next horizontal line is, we can actually reduce it to a very simple fact about perspective, which is what I mentioned earlier, which is that all parallel lines, actually, sorry, we don't even need that fact. If you notice something here, when we change perspective, straight lines remain straight lines. Changing perspective of an image of a tiled floor is never going to make a straight line stop being straight. And I hope that's something everyone can convince themselves of. When you look at, no matter how you look at a tiled floor, whatever perspective you use, whatever orientation you use for your picture plane, straight lines will always be straight. So if we just consider the lines that connect, that go between, so remember, this is a perfectly square tiled floor. It's a perfectly even square tiling of the floor. So there's another family of parallel lines we can consider here. And those are the diagonals. And if you imagine the diagonal line, for example, on this central tile here, it'll keep going, that line isn't drawn, but we can imagine it. And that diagonal line will go straight through the tiling, through the next tiling, through the next one. And everywhere that and not only are straight lines preserved, but intersections of straight lines are also preserved. So if we continue that diagonal up through, it'll go through this tile. And where is it going to hit the next line here? It's going to hit it at that corner of that tile, right? Because the intersection of that diagonal and that line is still going to be the intersection of that diagonal and that line, no matter what perspective we're in. So you can just draw this diagonal, and it'll tell you exactly where your next corner point is along this line. And you can draw a horizontal line there. And you can, if you want the next horizontal, you could draw a different diagonal and get even more horizontal lines. So just by drawing one of these diagonals, we immediately get, by seeing where it intersects all the vertical lines, it's at all of the corner points, and we immediately get all of our horizontal lines that way. So without going into the calculation of how these lengths are changing as we go up, we can immediately just dash off all of these horizontal lines without doing any calculations. So I'm not saying that there's something wrong with doing calculations, but also because if we're actually tasked with doing this, we don't have a measurement device, we can still complete this task. I mean, we needed a measurement device to do our horizontal, to find our horizontal corner points. But at this point, we don't really need to use our measurement device at all. We can just use the properties of these straight lines and their intersections. And we can mark off all of the horizontal lines that we need to complete our perspective drawing and extend it as far as we want towards infinity. So now as an experiment, as the final part of this experiment, what about this third image where, remember, we looked up and then we looked to the left. So now none of the lines appear parallel in our picture plane. And the really nice thing about this example is that you can complete it with just a straight edge. You don't need any measurement device. So you don't need any compass. You don't need, if you're using a ruler, you don't need to use the actual markings on your ruler. All you need is a straight edge. So all you need is a hardcover book. And because there's no distance, no longer means anything in this picture. There's no, we know that each of these tiles, all of those different edges have the same length, but they all appear differently. So our distance is not going to be measured in the same way. And that actually frees us up, surprisingly, and allows us to complete this one more easily than the others, in that we can just use our straight edge, not worry about measurement at all, but still complete the tiling. So given just this one tile, we can complete it into a perspective view of that entire tiled floor as far as we want. We can do as many tiles as we want. So as a quick exercise, can everybody try this right now? Maybe we could, Aniruddin, is it possible to send, or you could even, what you could do is if you're watching this on a computer, you could even just take a sheet of paper, put it on your computer screen and just trace this quadrilateral. And if even on a phone, it should be possible. If you zoom in, if you just put a piece of paper over it and trace the quadrilateral, you'll be able to get an image of this on your sheet of paper. And then I just want to see if everyone can try and extend this just using a pencil and a straight edge. And I'll give some hints, but to begin with, as a first step, everybody just try and trace this image onto your sheet of paper. So everybody can do that now. Basically, this is a very instructive exercise. So even if you think you have a sense of what to do, I think it's a useful exercise to try and actually do. So yeah, everybody try that now. And once you've done it, I'll give some hints as to how to proceed. So maybe just take a minute to actually trace this image onto your sheet of paper.
So I've sent you the file in the chat. Maybe just open Paint and.
Cool. You could also do it in Paint, exactly. So you can do it on fully digitally too. You don't have to do it on your physical paper. Either one is fine. Yeah, and just see, since you don't have many tools at your disposal, there's only so many things you can do. So you have a straight edge, you have your pencil, and that's it. So basically, you can extend lines that exist already. These line segments, you can extend them, and that's pretty much all you can do. And you can use when two lines intersect, you have a new point to work with. So you can connect that point to previously existing points. But that's really all you can do. You can extend lines outward, and you could connect points that exist. So right now we only have 4 points, but as you extend lines, you might get additional points to work with. So just using those basic tools, can we figure out a way to extend this tile further? And as a hint, I mean, to begin with, it might help to find your vanishing points. You know, we know that this is supposed to be a square tile, meaning that these two edges are both parallel to each other, so they should intersect. You know, when we extend them, they obviously will intersect, and that intersection represents the vanishing point of that family of parallel lines. Similarly, this one and this one represent parallel lines, so their vanishing point where they intersect each other represents the vanishing point of all parallel lines in that family of parallel lines. So using those two, can we manage to extend this further?
Yes, I think I got it.
Okay.
So first we extend the two parallel lines and the other two parallel lines.
Yeah.
Then the 2 points that we get.
I'll just pull it up so that I can show them what you're saying.
We join the. Okay. So first we extend the two respective parallel lines, and then we get 2 points. And
okay.
So we make the line joining those 2 points, and we make like this diagonal. The one of the diagonals, and where these two concur, we mark that point, and then we mark the other point which is not in that diagonal.
Okay.
So we get 2 or more points.
Cool. So I'll just try and show what you were saying. So you basically, can you go through it again? I'll draw it as you're saying it.
So we first extend the two respective parallel lines.
Okay. Okay. So we'll extend. Not perfect, but. Sorry. 1 second. Let me just use a different color actually. That's one set of parallel lines, and then the other one.
And then the other one.
Yeah. So you extended both of those parallel lines.
Yes. Now we got the 2 points, the 2 new points. Yes. Now we make the line joining these 2 new points.
Okay. Cool. Cool. And by the way, just some terminology. So these are both, we'll call them vanishing points. And what you've drawn, this line connecting them, we'll call that the horizon line. That's at least the terminology that architects and artists use, but it's a useful terminology. So what you've done is you've drawn a horizon line.
Yes.
Yeah.
Now we make the diagonal, which is kind of like parallel to this horizon line, and let it intersect that horizon line at some other point.
So, okay. So actually, rather than do that, why not do the other diagonal? Because that'll be easier in the sense it'll intersect in this page. So
okay, yes.
You could even do, so you were saying do the other diagonal, but I think this one will be a little easier because the intersection will be right here in front of us.
Yes, this one is also okay. So we make this diagonal and let it intersect the horizon line at suppose a point P. And then we join P to the other 2 points.
Okay. So 1 second. Actually, the screen share. Are you seeing I just drew the central one, but I don't think it's coming up.
No, we can't see the center line.
Okay, let me just try again. Is this not clicking? 1 second, sorry.
But do you want to restart your?
Yeah, I'll just restart this because I think it froze. Oh no. Okay, sorry, 1 second. Password.
Have you signed in from another device?
Oh. Let's see. 1 second. Have I? Okay, sorry. I think it's signed in.
Give me a minute.
It's saying only the host can share screen.
Give me a, I'm making you the co-host.
Okay.
I've made you the co-host. You should be able to share your screen now.
Okay.
Yeah, we can see your iPad now.
Great. Okay, cool.
Okay.
Sorry about that. So basically, so the next step is to do this
Yes.
central line. Yeah. Sorry, continue.
Okay. So now let the intersection point be P. So we join P to the other two vertices of the quadrilateral.
Okay, cool. So you're saying this is this intersection point, and
Yes.
you're joining it to this.
Yes. Now, yes. Now this point that we got two more points. So suppose that the left one point is P, and the point where the horizon and two parallel diagonals concur is Q. Then we make PQ.
Okay, you're saying that the left, this one is P,
Yes.
and which one is Q?
The point where the horizon line and two parallel quadrilateral lines concur. Right one.
Okay. The two. So you're one of these, this one basically you're saying, or?
Yes.
Okay.
Yes, this one.
Okay.
Now we join PQ, and then this is the next quadrilateral.
Yes. Cool.
Okay.
And then
in a similar way we can.
Exactly. So basically you've created one new quadrilateral here. I'll just draw it in black so it's a bit easier to see. But you can see that this gives us a second quadrilateral in our tiling.
Yes.
And in this way, as he said, we can continue and we can go as many more steps as we want. So you can very quickly do a third and fourth one, for example, by just connecting the other horizon line point to, to the other new point that we created. And now we suddenly have 4 points in our, 4 quadrilaterals in our tiling. And again, all of this is done without any measurement whatsoever, and just using the ability to extend lines. And you can see how you could easily continue this indefinitely and get more and more points. So it's a kind of fun technique to try. And the key idea here, again, was that this diagonal that they just made, it hits the horizon at a third point. Maybe I'll call this P and this Q. So P and Q are the first 2 horizon points that we saw, which represent 2 different families of parallel lines, which are the different edges of this tile. And the diagonals, they give us a third family of parallel lines, which intersects at a third point on the horizon. So each of the horizon points represents a different set of parallel lines on the floor. And using just that idea, we can continue this process. So, so let me just switch. So sorry, I'll switch back to the other device now. Hope it doesn't create too many problems. And Sorry, 1 second. Okay, so I think, can everybody see my screen again? Okay.
Yep, it's good.
Cool, cool. Yeah, so hopefully that makes sense. And you can imagine you can complete this picture. You can just keep adding more and more lines just using these 3 points on the horizon and get as many tiles as you want and using only a straight edge. So that's quite exciting. And there's a couple natural questions to ask at this point. One is, why does this picture look so realistic? Why is it that the tiles have the same, how is it we know that the tiles have the same size, despite their depictions having different areas? And the answer is related to some things that have been mentioned by some of you already. And the second natural question is, why is it that this view of the tiled floor is easier to draw than the other two? You know, it's the view in which we lost all the information about the lengths of the sides, and yet somehow it became easier in some sense. So the second question, you know, it's not so precise, so it also, I'm only going to give a vague answer, but you know, if you imagine this tiled floor and you imagine a camera dangling above it, maybe if you were to just let the camera wobble around and take a picture at a random time, you're much more likely to get an image like that third image, in which there was no obviously parallel lines. I mean, no lines that looked parallel, and there was no measurements preserved. So in that sense, it's the most general position. It's the most general way you could position your camera. And the first two ways were actually much more specific. There were many more constraints. I mean, there's a much stronger constraint, because if you just randomly take a picture, you're not going to have, it will look like the third version. You have to really specify that you want your picture plane to either be parallel to the floor or at least have an intersection with the floor which goes along with your tiling, if you want the first image or the second image. And if you were to just take a picture without thinking and do it randomly, you would basically get a third image. So it's the most general position in that sense. And in some sense, because at the same time, we're having a lot more, we're having this tool in the third version of these points at infinity, these vanishing points, which we can use to draw all the rest. So we suddenly get that tool at our disposal, which we didn't have in the first two cases. So I mean, so that's all I'll say about the second question. But for the first question, why it looks so realistic, we can say a little bit more about that. Why is it that we know that these tiles have the same size, despite their depictions having different areas? So to answer that, I want to look at the even more basic question of what changes when we look at the tiled floor from different perspectives. What stays the same and what changes? What's preserved and what actually changes a lot and doesn't end up mattering? So what do these images have in common, these three images? So although the distances and the angles change, something obviously has to stay the same when we're changing perspective, because we know that these all represent the same grid. So what are some things that remain the same? One thing that we know stays the same is that straight lines remain straight. We already mentioned that, and we used that already in these exercises. There's no way that when we change the perspective, a straight line is suddenly going to become a curve or anything like that. Straight lines remain straight. And intersections remain intersections. If two lines were intersecting here, then they'll continue to intersect here. Similarly, parallel lines remain parallel or start meeting at that horizon, somewhere along that horizon. So there's something special about that horizon, but basically, if they're parallel, they'll end up either remaining parallel, like when we went from the first image to the second image, all of those horizontal lines remained parallel. But all the vertical lines, suddenly they went from being parallel to suddenly appearing to meet at that horizon line. And then in the third image, everything started meeting at the horizon. So basically, let's try and pretend for a second that these vanishing points, or these points at infinity along the horizon, let's imagine that they're actually not imaginary, but that they actually exist. And that the horizon line is an actual line which contains all of these points at infinity. So in a way, things become really elegant now, because any 2 points in this picture plane determine a line, and any 2 lines intersect in a single point. Either either on the horizon or off the horizon. But any two lines will intersect in a single point now. Well, almost. So we may have to turn a little to see the point at infinity where these formerly horizontal lines meet. So for example, in that first image, it's not quite the case that any two lines intersect in a point. If we look at the horizontal lines, they just keep going and they actually seem parallel. But if we turn our head a little bit, suddenly they start meeting in a point. So if you allow yourself to wobble a little bit, any two lines will meet at a point. So then what's actually happening here? What is this structure we're imagining where we have any two lines meeting in a point and any 2 points determining a line? And can we clarify that a little? Can we find a geometry in which any two lines always intersect in a point and any 2 points always determine a line? And if there is such a geometry, such a geometric structure, it probably will help us understand our vision. It seems, because our vision seems to have that property more or less. So maybe we can model our vision on that. So there is such a structure, and it's called projective space. And it's actually really, as you might expect from these very simple laws that I just mentioned, it has some very simple axioms which determine projective space. And the first of those axioms is that any two projective points are contained in a unique projective line. In other words, any 2 points determine a line in projective space. And any 2 lines contain a unique projective point. In other words, any 2 lines will intersect in a point somewhere. So that the first one is anyway true of Euclidean space. Any 2 points always determine a line. But the second axiom is where we depart from Euclidean geometry a little, because in Euclidean geometry, any 2 lines either intersect or are parallel. Whereas now, any 2 lines contain a unique point, intersect in a unique point. And we need a third axiom just to make sure that there's enough points. This one's a little bit more, sounds a little stranger at first, but basically the axiom says that there's at least 4 projective points, no 3 of which are in a projective line. So for something to be a projective space, it has to contain at least 4 projective points, which are no 3 of which are collinear, because otherwise we won't have enough points to work with and we won't get anything interesting. So this is kind of a silly one, but it just guarantees that we have enough points to work with. There has to be at least 4 points. In other words, there has to be a quadrilateral, is another way of thinking about it. At least 4 points, no 3 of which are in a line. So we have to have one projective quadrilateral to work with, and then we're good. So, but what are we actually talking about here? What I talked about a space. I know that, everyone here in the audience are from different backgrounds. So some of you, this might seem really obvious. For some of you, it might seem like, okay, what the heck am I doing? So frequently in math, we define a space more abstractly than you might be used to, because when we say points, we're not necessarily talking about points that you draw in your Euclidean plane. More abstractly, the points of an abstractly defined space are just the most fundamental indivisible components of it. So, for example, we can define and even work with something like the space of triangles, the space of all triangles in the Euclidean plane. And we can consider that as a well-defined space whose points are the different triangles in the plane. Each triangle in the plane represents a point of that space, and then we can start working with that space in different ways. Or as a totally different example, you can think of the space of configurations of a physical system, like the space of, you could look at the space of states of a particle in 3-dimensional space. A particle has position and momentum, for example, so that you could look at the space of states of that particle, which would just be the space of states of different positions and momentums of that particle as it moves about. So we can abstractly define a space in that way, where the points are just the most basic unit things that make up that space. And if this is new, it's something you will work with more. So it's okay if it doesn't fully make sense, but it'll be useful for what we're talking about now with projective space. So what I want to ask is whether this projective space, which is given by these 3 axioms, whether that actually exists, or whether maybe these axioms simply don't give us anything meaningful because maybe they contradict each other, maybe there's no such actual space that fulfills these axioms. So does a projective space actually exist? Is there any space that satisfies those three axioms? And indeed there is, and here's a recipe that we can use to cook up a projective space. So now let's imagine R3, three space, and let's just fix a point in R3, a point A. And let's define our projective points to be all of the lines through that point A in R3. So a projective point simply refers to a line in R3 that goes through A. If you want, you can think of A as being the origin, if that helps for now, but actually in a second, we're going to pretend A is away from the origin. So maybe just let A be any point in R3, an arbitrary point. We're looking at all of the lines through A. Those are our projective points. And if those are our projective points, what are our projective lines going to be? So this is just remember that a line in general, in our general way of thinking, a line is a bunch of points that I guess you could say, one way of thinking of a line is taking a point. If you're in R2, it's to take a point away from the origin, and then just think of it as a vector, and just think of all of the different scalar multiples of that, and that creates your line. So it's a way of taking a point and just scaling it by arbitrary scalars, kind of extends it into a line. Or another way of thinking of it is if you were to just so in a similar way, if a projective point is a line through A, then a projective line, it makes sense to think of that as a plane through A. So it's a collection of lines through A, which are related to each other in that they all sit inside of a plane. So we're defining it that way. And finally, we'll define projective space to be the set of all lines through A in R3. And this structure, projective space, we'll call it the real projective space of dimension 2, just to be a bit clear. That's how mathematicians usually refer to it, RP2, or the real projective space of dimension 2. So it's the set of all lines through A, and the points of projective space are just the lines through A. The lines in projective space are really the planes through A in R3. So does this structure, does it satisfy our axioms? Remember our axioms? The first axiom is that any two projective points are contained in a unique projective line. And that means that given any, so what are projective points? They're lines through A. So here's our point A, here's one line, here's another line, and any two projective points have to be contained in a unique projective line, meaning they should be contained in a unique plane through A. Is that satisfied by two lines through A? Yes, it is, because any two lines through A, will determine a plane. So any two projective points will determine a projective line, right? Any two lines through A determine a plane in R3 through A. And similarly, any two projective lines, in other words, any two planes through A, ought to contain a unique projective point. So any two planes through A ought to contain a unique line through A. So is that the case? Given two planes in R3 going through the point A, will they contain a unique line through A? And the answer is yes, because any two planes will intersect in a line. And unless these two planes are not parallel to each other, they're both going through the point A. So they will have to intersect, and they'll have to intersect in a line. They're distinct planes, they're not the same plane. And that line, since that's the full intersection of these planes is that line, it'll have to contain A, since these are both planes through A. So in other words, any two projective lines will contain a unique projective point. Finally, just to make sure our last axiom is satisfied, are there four distinct projective points, no three of which are in a single projective line? In other words, are there four distinct lines through A, no three of which are coplanar, no three of which are in a single plane together? This one's a little harder to imagine, maybe without writing out some vectors. So I'll just give a hint. as a hint, let's look at our standard way of thinking, our standard frame for R3. And we can consider the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, the 3 unit vectors, and the vector 1, 1, 1. Imagine those vectors all based at A. Each of them determines a different line. So each of them determines a different projective point. And no 3 of them will be in the same plane, right? These 3 are all obviously creating a full frame of R3. The first 3 are not coplanar. And you can convince yourself, if you look at it a little bit, that if you take this other one along with any 2 of these 3, that will also not be coplanar. That'll still span all of R3. So I'll leave it to you to think about it a little more, but basically we have 3 distinct projective points from these, which are no 3 of which are coplanar. So we have enough points to work with. So RP2, the projective plane, it satisfies the axioms that are inspired by our vision. These axioms came from looking at how we see lines in space and how these lines seem to intersect and meet at infinity in our vision. And it's interesting that this set that we just described satisfies those same axioms that were inspired by just looking at perspective and how we see things. But it's not a coincidence, because it really captures the idea of viewing the plane from an all-seeing eye based at that point A. In other words, the lines through A can be thought of as our lines of sight, which connect the eye to the points it sees on the floor below. So imagine that tiled bathroom floor, we're looking at it from above, and our lines of sight are when we take a picture, we're basically looking at where our lines of sight are meeting that picture plane. So in particular, all of the different points on that tiled floor, when we're looking at it, correspond to different lines of sight of our vision. And if we want to think about the set of all the lines of sight of our vision, that basically corresponds to all the points on the floor, if we extend that floor as a plane to infinity. But that floor doesn't account for all of our lines of sight. There's some remaining lines of sight, namely the horizontal lines of sight. So there's still lines through A which don't hit the floor, and those are precisely the horizontal lines through A, which are points of infinity at infinity, and together they form a line at infinity, which is that horizontal plane through A. So really a perspective drawing or a photograph is simply a way of capturing the points of RP2 as points on a fixed picture plane. So in our first picture, you could imagine the picture plane being parallel to the floor, and we can think of that picture plane as a projection of RP2. We're getting most of the points of RP2 in that picture plane, except for the ones that were horizontal. There's still points of RP2 which are horizontal lines through A, and those don't get represented in the picture plane, but everything else does. And in a way, RP2 is really capturing all the possible perspective views at once, without specializing to a given picture plane. So, our earlier perspective views, the first one, you could imagine the picture plane being horizontal. The second one, where we looked up a little bit, you could imagine the picture plane being vertical. And the third one, you could imagine the picture plane rotating a bit, so it's no longer parallel to any of those grid lines on the floor. So each of those perspective views is kind of a specialization of that whole projective space to a given picture plane. But projective space itself is capturing all that information at once. That's the really cool thing. So all this can actually be described really nicely using homogeneous coordinates. I think since I don't have much time, I'm gonna skim over this a little, but basically using homogeneous coordinates, we can very quickly make calculations involving RP2 and even prove many of the things that we've been hinting at. So, but just to give a quick overview, when I say homogeneous coordinates, I mean that a line through the origin, if we're looking at R3 and imagining the origin, any line through the origin is determined by a point ABC, but it consists of all the points that are scalar multiples of that point, of that vector ABC. So in other words, it consists of all the points TA, TB, TC, where the T parameter runs through all real numbers. And it's easy to check that we can create an equivalence relation between points where we say that ABC is equivalent to TA, TB, TC. And we can denote that equivalence class this way, A colon B colon C. So that's what I'm calling a homogeneous coordinate representation of a line in RP in 3 space. And yeah, I think we'll get into that. We can, if we did another lecture on this, we could talk about that more. But right now, just to go back to some of the original questions we asked. We've been looking at tilings so far, which are stuck to the ground. But actually, perspective is useful for depicting things above the ground as well. You can, if you can easily draw boxes, houses. You can draw a city just using some of these basic rules of perspective that we talked about, of having vanishing points on the horizon and just playing from there, expanding from there. And there's nothing special about the horizon. The fact is, any 2 parallel lines, any family of parallel lines will converge to some point in your picture plane. The only thing that's special about the horizon is that that captures all of the families of parallel lines that are parallel to the ground. So when you have, that's why in our grid, in our bathroom floor, all of those 3 families of parallel lines that we looked at all vanished on the horizon line. But if you take a family of parallel lines that's not parallel to the floor, they'll also converge to a point in the picture plane. It'll just be a point that's off of the horizon. So again, this is something that's very easy to prove if we just use our homogeneous coordinates, but I think we'll skim over that. And you can see from this picture, for example, which is of a city, but from above, you can see how there's vanishing points on the horizon, which are kind of off of our picture, but you can imagine that horizon line somewhere here. And there's also vanishing points off of the horizon. If you look at where the buildings are the vertical lines of the buildings are converging to some point down here somewhere. So that's just an example of how you can have vanishing points off of the horizon. So there's nothing that special about the horizon line. It's just that that's where all of the families of parallel lines that are parallel to the ground converge. So, and more generally, if you take any plane in actual space, all of the families of parallel lines on that plane will converge to a single line of infinity, which you can call a horizon line. So you can define a horizon line that way and have different horizon lines as well. So, just to go back to another classical painting drawing by Dürer, there's lots of families of parallel lines here. Can you find any vanishing points that are off of the horizon? And there's various different, they're a little harder to spot, but for example, if you take diagonals of these windows, those will be parallel to each other and they'll converge to vanishing points off of the horizon. So not all vanishing points are on the horizon. That's an important thing to remember. Now, let's try and actually explain why parallel lines appear to converge. Now that we've done all of this, let's go back to a much simpler question and also also see where they converge to. So I think that even the key point here is that not just that parallel lines converge to each other, but that any line, if you imagine, in wherever you're sitting or standing now, just look at any line in space, maybe the place where your ceiling meets the wall of your room. And just imagine that line, just keep following it along as it extends to infinity. It's a bit of a stretch of the imagination, but it's actually, it's easy to do if you have a laser pointer, for example, or something, but you can just imagine a laser pointer now since we don't all have them. And just imagine moving it along a line in space, and just imagine that that line is extending on to infinity, and you keep moving your laser pointer along it further and further. How would that trajectory of that laser point appear in your vision, in your picture plane? And one thing that maybe it's obvious, maybe it's not so obvious, is that even though the line in space is going on and on forever, if you imagine it going on and on forever, in your picture plane, it won't appear to go on and on forever. It'll eventually converge. It'll eventually stop moving somewhere. And one way to see that is, again, just imagine that your head is fixed in place, and imagine that you're following, again, maybe it's easy to imagine with a pretend laser pointer. Imagine that your axis is fixed of your laser pointer, and you're just following that line along in space. And you're moving your laser pointer along, that point is moving along the line, and it'll keep going and going and going. You can keep following it, but clearly at some point, you're gonna lose it. I mean, even if it's going on forever, even if you have perfect vision, it'll take smaller and smaller movements to move, a foot down that line. At some point, the smallest movement of your finger is gonna move miles and miles along that line in space. And eventually, however, you're gonna lose, your point is just not gonna be on that line anymore because your laser is gonna be parallel to that line. As you move your laser along a line in space, eventually your laser is gonna be parallel to it, and then it's not gonna intersect it at all. But up until then, it's going to keep moving along it. So that's a way to see where that line will actually move off to, where its vanishing point will be in your picture plane. It's where your laser would eventually move off of it and where that laser would be intersecting your picture plane at that point. Sorry, I don't know if this is making much sense because it's a lot of imagination here. But basically, the point is that any two parallel lines will eventually converge to points on your picture plane. And in fact, they'll converge to the same point because they'll converge to the point that your laser pointer is pointing to when it keeps following them along to infinity, at which point it's parallel to those lines. So maybe ask a question if this is not making any sense at all. Sorry, I don't know if this is, when I've given this talk earlier, I did it with an actual laser pointer in an actual room. So it kind of worked a little, but I think, but maybe this explanation is a bit harder to follow on Zoom. So, but the basic point is that if you, in your room, you'll have parallel line, like a family of parallel lines consisting of where your ceiling intersects the two walls on either side of you. And those will eventually, in your picture plane, converge to one point. And that point, a way of seeing it is to just follow either of those lines along in space indefinitely, using a pretend laser pointer, for example. Or we could also think of this using homogeneous coordinates. So for those of you who have seen something with this before, you could imagine that a point P is some point in R3, and that you have a vector v1, v2, v3, which is any vector that's not parallel to this horizontal plane z equals 1. And just imagine that we're looking further and further out along that line. The line being L, which is defined to be P, the point, plus TV. So as T is our scalar that goes along all real numbers, we're spanning out a line in space. P plus TV is this line in space that we span out as our parameter T goes across the real numbers. And at time T, we're seeing the point P plus TV1, P2 plus TV2, P3 plus TV3, but I'm writing it in homogeneous coordinates because I really want to imagine this in the picture plane where z is equal to 1, this horizontal plane where z is equal to 1. And because I'm working in homogeneous coordinates, what I've written here on the left and what I've written here on the right are actually the same point. They're the same point in projective space. Because on the right-hand side, I've just divided everything through by P3 plus TV3. And I know I'm not dividing by 0 because I'm choosing a vector which is not parallel to the plane ZB1. So except for maybe some, so basically most of the time this is well defined, and I can divide through by this quantity, and I can write my point that I'm seeing in the picture plane at time t in this way. And as t goes to infinity, this expression will simplify to v1 over v3, v2 over v3, 1. So that's a point in my picture plane. That's the limit as t goes to infinity. It's basically the vanishing point of that line that I'm following. So it's independent of the point I started with. And meaning that I could take any parallel line, any line in that family, starting at any point in space, follow it along by that vector v, follow it along And as t goes to infinity, I'll get the same point in the picture plane, the same vanishing point. So, so this is the vanishing point not only of the line L, but of all lines that are parallel to L. So I think I'm very much out of time. So what I'll just say for further exploration, there's some nice information that I based a lot of this talk on in this book by John Stilwell called The Four Pillars of Geometry. So you can look there if you want to see more about projective geometry or RP3 or the cross ratio, which I would have liked to talk about a little bit, but it's the actual quantity that's preserved when we're changing our perspective. And it's really a ratio of ratios. So the one way to say, if we look at that tiled floor, you could take any four, the cross ratio is a quantity that we can define on any four collinear points. So with that tiled floor, you could take any four collinear points on any of those horizontal or vertical lines, and you could calculate the cross ratio. And it's a very easy thing to calculate just based on the lengths, the respective lengths between those 4 points. And that quantity will be preserved no matter how we change our perspective. So for example, for an even square grid, the cross ratio is 1. Basically, if you take four collinear points that are spaced 1, 1, 1 apart from each other, their cross ratio will be 1. And you can calculate in any of those different perspectives, the cross ratio will still be 1. So the fascinating thing is that our brain is actually, in some sense, calculating cross ratios constantly, because it knows that those perspectives are all of a roughly similar grid. And the only way to really know that is via this quantity called the cross ratio. So even though it's a ratio of ratios and it's something that feels a bit abstract, it's also something really built into the way that we see space and the way that we process our visual input. So unfortunately, there's no time to get into that now, but it's definitely something worth looking into if you haven't heard of it. And for those of you who have seen it in, say, complex analysis, I think it's nice to see it from this perspective in this more elementary way. So I'll finish there, but I don't know if there's any time for more questions. I'm happy to take questions, but Anirudh, maybe you can say if there's how much time we have.
Absolutely. Maybe before you get to questions, so huge thanks to you for crafting this wonderful session. So it is like amazing how you captured the entire audience's attention so effortlessly, like making everyone go from, wait, why should this happen, to, wait, isn't it obvious? So thank you very much for that. This was absolutely a lovely session. So there is one question in the chat. So do post your questions in the chat or unmute and ask once this question is done. So I'll just read out Arunangshu Karmakar. Is it possible to distinguish between a square and a rectangular grid by seeing a perspective line diagram of the grid?
By seeing a perspective line diagram of the grid. So you're asking if, yes, so it is possible. That's a good question. So I think, just to reiterate the question as I understood it, let's say that we were starting with a square grid, but suppose we had started with a rectangular grid. So maybe the vertical segments are all unit 1 and the horizontal segments are all have length 2 units. So imagine that that's the basic shape in our grid, these kind of rectangle shapes. And if we then take a perspective view of it, is there a way to know that that's not a square grid and that it's actually a rectangular grid? And the answer is yes, it is possible. And the answer is using the cross ratio, we can figure that out. Because with the square grid, we can take any 4 collinear points in that grid in any perspective along any of the horizontal or vertical lines. And we'll always get that same cross ratio being 1. And whereas with the rectangular grid, we won't. So using the cross ratio, we can do that. We can actually figure that out.
Okay, thank you, sir.
So there was one more question I got in private chat. So it said, what if we take the projective space of the projective space? How would that look?
So taking the projective space of the projective space isn't such a well-defined thing. Basically, here, maybe what you're saying is if we take the set, so the way I define projective space is the basic points where it was the set of points in our Euclidean space through a given point. That was the basic points of projective space were those. So that's kind of our building blocks of projective space. So now, what if we now look at the set of points, set of lines in projective space? So I don't know if that's what you meant, that's something we can do. And if you look at the set of lines in projective space as our basic points in a new set, in a new space, then we're really looking at the set. Lines in projective space are just planes in Euclidean space through a given point. So now we're looking at the set of planes through the point A, for example, in R3. And yes, we can definitely do that. That is a well-defined space, the set of planes through a given point in R3. And interestingly, that space that we get, so the technical name for it is, I guess, the Grassmannian of planes in R3. But in this case, it's actually equivalent to that projective space that we originally formed. So it's actually the dual of that in a way. But it's fully equivalent to that initial projective space that I was describing in this case. So if we're working in R4 or like in R5 or other Euclidean spaces to create our projective space, it becomes a little more complicated. But I don't know if that's answering your question. I don't know if that's what you meant by the projective space.
I believe it does, yes. Yeah. So I think we now come to a formal close of the session. So once again, so there's a question from Arnab Chauhan. Could you tell about perspectives for a parallel curved grid, that is parallel sine curve grid?
Oh, a parallel sine curved grid. So I have no idea off the top of my head. If so you're saying a curved grid where you're using sine waves has at least one of the two things. So I don't know off the top of my head at all, but it's an interesting question. I mean, and that's an interesting class of questions. How do different shapes change under perspective transformations? So maybe that opens up a few questions that are kind of fun questions to explore if you want to think about this more. Given a shape, like a square, what are the different shapes you can get by looking at it from different perspectives? Right? And for example, you'll obviously get different quadrilaterals. You can get a trapezoid, you can get different things, but can we get anything? Can we get any quadrilateral that way? So the answer is actually yes, but it's not so easy to see. And that's an interesting thing to think about. Another question, what are the different things you can get from a circle from different perspectives? And so there's related questions to that. And in a similar, so maybe I'll just throw those out as questions to think about. What shapes can you get from a known shape through perspective transformations? With a sine curve, I'm not sure off the top of my head. My guess is that we'll just get other sine curves. I mean, other curves that are still sine curves, but with different parameters. Okay.
And there's one question from Sohan Biswas. Can we get projective spaces from geometries other than those Euclidean?
So yes, in some sense you can definitely, because algebraic geometers work with that all the time. So you can start with other kinds of number fields. I mean fields besides the real numbers, and create. I mean to begin with, you can look at so there's an operation that people use in the field of algebraic geometry, which is to projectivize something, projectivize a space. And you can do that with all kinds of non-Euclidean spaces as well. So yes, I guess the short answer is you can.
Okay, so I think once again, so a huge thanks to Dr. Vijay Ravikumar for this wonderful session, taking us all from basic intuition to what we see every day to linear algebra and some amount of a hint of algebraic geometry, and it was an amazingly crafted session. So thank you very much for this lovely session. So we'll next meet at 5:30 p.m. When Professor Nutan Limaye of IIT Bombay will be giving yet another interesting talk titled "The Charm in Proving Something is Impossible, a Complex Theoretic Point of View." So do join us then at 17:30. And the last talk for day one is by Professor Kavita Ramanan of Brown University, who will be talking on tails of randomness. So I hope to see you all there. And once again, thank you for attending, and thank you, Dr. Ravikumar, for this session.
Thank you very much.
Thank you, Professor, for accepting our invitation. Thank you.